Right.
Okay, thank you. Let me first thank the organizers for this wonderful opportunity to be here and to share some of the recent progress in one area of the Hawaiian physics, mainly about the CME search. Well, as many of you know that the recent interest in the intersection of nuclear structure and energy collision was motivated by this isobar collision experiment. And the isobar collision experiment itself was motivated by the search of CME, which I will explain. I hope that's explain a little bit why I'm here. Okay.
Look on the screen.
Oh, yeah.
What do you mean I should
So you point at the arrow, then you click, and then you draw the arrow. The next will be fine. Yeah. Try again a little bit.
Okay, it's perfect. Fine. Yeah. So here's the talk. I understand that many of the participants here perhaps are not very familiar with this current magnetic effect. So I would like to spend a little time explaining why we're so interested in this effect. And then I also will explain why that search for this effect in Hawaiian collision is so difficult. After that, I will discuss what have I learned so far from the first step isobar collision result. I think even for people in Hawaiian field, many of you are perhaps not particularly aware of the latest status. I would like to, tell you what we think we understand. And then I'll end up with a little bit discussion of where we can work next. Okay, a little bit introduction. I'll start with this quartz cosmos. Many of you know, for this is a standing theme of the APS April meeting. They always like this theme, quartz to cosmos, for the reason that they want to showcase that the physics encompass everything from the smallest scale to the largest scale, and also that physics is intrinsically connected between quark and the cosmos. For our field, meaning Hawaiian physics, the cosmos is equal to basically the quark, or the more precisely a hot quark and gluon soup. If you trace back to the very beginning of our universe, of course, there was a time when the cosmos indeed would be just a hot tube of quark and gluon. The quark gluon plasma, of course, that was ongoing in the old time, but in Hawaiian collision, essentially what we want to do is, in some sense, like doing a condensed matter experiment of QCD, we try to change external conditions like temperature, energy density, things like that by colliding large nuclei together. And we know pretty well, from that QCD calculation that when you do that, and when you have a high enough temperature on the water, 10 to 12 Kelvin, you will switch from your, regular, usual cold hadronic stage or phase into a new phase of matter, and that's called quark gluon plasma. These are some of the curves from last QCD calculation that show that there is a crossover, not a true phase transition, but a crossover from hadronic side to the quark side. In doing that, we also have restoration of the one of the very important properties of QCD, namely the chiral symmetry, which was spontaneously broken in vacuum or low temperature, but that will be restored in high temperature. Okay, so far everything quite general. And of course, you can see that this is a plot from a cosmic evolution model. That's where we are now. Okay, and if you trace it all the way back, then that's about 10 to the minus 6 seconds, and the temperature was high enough, around this scale. Okay, and that is where our quark gluon plasma used to live. Okay, so it's really an old phase of matter, if you wish. So the big bang was gone, but we have the little bang at relativist Hawaiian collider and the large hadron collider. So what we do is like kind of yesterday once more, we want to recreate that environment. We want to study the physics that could not be accessed easily in the hadronic world. Okay, so what's the difference between now and then? Okay, that's the important question. Then means in the early universe, now it means our usual hadron and nuclear world. I think there are many differences, of course. But I want to highlight two important differences. One, the missing QCD chiral symmetry. But we all know that our budget of energy and matter in the world or in the universe is such that we have only 5% of ordinary or visible matter. Out of that 5%, 99% or more is perhaps from the nuclear mass. Okay, and where does that nuclear mass come from? It doesn't come from something like Higgs mechanism. It actually comes from QCD interaction. Okay, so that missing QCD chiral symmetry is actually crucially important. So we don't have it today, but we do have back then. So that means at high temperature it will be restored. Okay. Another important difference between then and now, that is the matter-antimatter asymmetry. Our world is built by baryon, matter. We don't have many antimatter around. But if we do have, that will be a disaster because they're going to annihilate. You trace this asymmetry all the way back then, you would realize you would need a mild breaking of that matter-antimatter asymmetry, even back then, on the order of like 1 out of 10 to the 10. Okay. But even for that tiny asymmetry, we don't have a known easy mechanism from the standard model to give you it. Okay. So in other words, we need some more safety violation at the beginning of the universe. And I'm going to argue with you that the study of chiromagnetic effect helps understand both of these fundamental issues. Okay? And that, of course, these issues are crucial for understanding why we are here in today's universe. Okay, so a little bit basics about you can see that for chiromagnetic effect concerns the chirality of quarks. The chirality quarks, you start with direct, fermion Lagrangian. You can either separate them into a left-hand and the right-hand sector if there's no mass. This axial symmetry is a classical symmetry. It means basically specific correlation between a quark momentum and spin, but a large mass term easily spoil that. Okay, I think these are some textbook stuff. I'm not going to spend time. But what is a little bit different in QCD that in addition to a possible standard model mass for the light quark, which is very, very small, negligible, but you do have a large chiral condensate, as I already mentioned. Most of the mass in the vacuum come from that chiral condensate. So that's a huge effect. But if we are able to go to the high temperature and eliminate this term, then we're almost in the chiral case, okay, for the U and V flavors. So that means that this could serve as a possible way of probing that restoration of chirality. Once you have that chiral restoration, the story doesn't stop here because our U1 axial symmetry again broken. Not through the chiral constant, but through the chiral anomaly, meaning that if you quantize the theory, that is gone. Okay. So the question here is that how do you have a way to access that information, that chiral anomaly, in the context of quark-gluon plasma, where we know that there is chiral symmetry restoration? Again, I'm skipping details, but here is the simple way to kind of convey to you what we want to do. All the microscopic symmetry will show up in your macroscopic matter property. Okay. For example, a lot of talks are about hydrodynamics. Why you have hydrodynamics? Well, hydrodynamics are just conservation of energy momentum, and that comes from your microscopic theory having that symmetry, okay? Having that space translation and time translation symmetry. Now we have a very peculiar situation where we do have a microscopic anomaly, which means it's like a symmetry. Not a full symmetry, but it's not like totally non-symmetry, okay? So it's like something like a symmetry. And you ask, what could be a consequence of or a way to reveal that at macroscopic level, because we study macroscopic matter for gluon plasma. And the answer is the chiromagnetic effect. Okay, so this is that effect that we're looking for. It says that if you do have a system of chiral fermions like our light quarks in a high temperature phase, you apply a magnetic field. This is a QED or maximum magnetic field. And then that will induce at a macroscopic level a transport current, which is basically a vector current with electric current. So this is really a very weird transport process. Because our normal electricity, like you turn on a voltage or electric field, you get an electric current. Now this is totally different because when you turn on a magnetic field, you get an electric current. And you can see naively it even violates all like about parity or CP and so on. But the very reason why this happens because you have this guy here, which I call mu5. That mu5 quantify the difference between the right-handed fermion and left-handed fermion in your system. In other words, you start with something like what we call chiral material, chiral matter. Its mirror image is not itself. And when you have an environment like that, you do have this process, transport process. Okay. As I said, it requires macroscopic chirality, meaning that you have a different number of right-handed and left-handed fermion in your system. So how to intuitively understand this effect? Well, it's not difficult to understand. In the most intuitive way, you can think of it like this. When you apply a magnetic field and you have charged fermion like a quark, well, quark has spin and it has magnetic moment. So your magnetic field will polarize your spin. Okay. So let's say you have a U quark magnetic field this way, your spin will be preferably along this way. Okay. And then if you also have chirality, say you have only right-handed quark. As I already mentioned, chirality means your spin and momentum of your fermion has a correlation. If your spin is this way, your momentum is this way. So now you combine the two correlation together, you realize that you get a momentum correlated with your magnetic field. Well, momentum of a charged particle that forms a current. Okay. So that's an intuitive way to understand what happened. But quantitatively, this coefficient you can see is a very, very simple coefficient. It arises from the fundamental anomaly. Okay. Yeah.
Can I ask you? So the anomaly, where does it come in this picture? In the middle where you create this imbalance, or in the?
Well, that's a very good question. It actually, so to say, it appears twice. First of all, I'm going to come to that point, namely where you get this mu effect. That will come from anomaly. And secondly, suppose you're given that mu effect, the imbalance, you calculate this effect, you will see this coefficient itself is dictated by anomaly. This coefficient also is basically the anomaly coefficient.
So in both ways.
Yes, yes.
Okay.
Yeah.
So there was some question in the last group right here when we decided how the spin get relaxed to align with the beam. There must be time scale, right? It's
You mean like the yes?
relax to actually align with the B direction. Is this how do you know how to estimate that?
That's a very good question.
Controls that?
That will depend on your specific setting. I think what you said is more like, say, suddenly you turn on the magnetic field, and then how the spin will evolve toward that.
Yes.
That's a good question. I think if you assume that time scale, well, again, depends on, you're right, that time scale will affect whether this process is more like a hydrodynamic regime or more like in a transport regime.
Yeah.
So I don't have an immediate simple answer.
How do you, in the current model, you just immediately instantaneously assume the alignment? Or there are some
right. Yeah. I think that's what usually is assumed. Yeah. Which perhaps is true because spin is a very, very fragile quantity. It perhaps reacts.
But there's a lot of thermal motion also, right? You have temperature, you have a lot of like stuff that try to probably destroy this alignment.
First, I mean that's right. I mean, if it's really out of the hydro regime, yes, that's a concern. Okay, so then coming to this question of how you get this mu phi, because as I said, this effect requires you do have some correct imbalance, and then that comes from another aspect of the anomaly Liao already asked. So it comes from the Q3 topological fluctuation. Well, again, I don't want to go through all the details, but just want to mention that it's very important for the non-produced properties, QTD, in particular in the vacuum, like characteristic breaking and so on. So those kind of topological winding of your gluon field, they induce anomaly which give you that chirality. So first of all, there are all those gluon topological fluctuations, and those topological fluctuations, the gluons will turn into the chiral anomaly, through the chiral anomaly, turn into the difference in the right-hand and left-hand fermion. So this is very famous in mathematics. It's Finger's index theorem. In the context of QCD or long-abelian gauge theory, what it means is that your topological index is basically your topological winding number of your gluon field configuration, which is like the Mobius, right? And then the ends are just like the quarks, which will flip their chirality. In this picture, it means that it goes from the inside of the strap to the outside without noticing it, and that's this net chirality being created in those kind of topological fluctuations. Okay, so you can see that. So what is the story in short? We think that in the QCD, there are large topological fluctuations in the gluon field, and that topological fluctuation, which is our schematic represented here, will create what we call the chiral asymmetry. Namely, your right and left hand fermions in the system are not balanced. And that chiral asymmetry can turn into a measurable effect, namely the chiral effect. And this has a direct analogy with the baryon symmetry process that I mentioned earlier. Okay, so one of the most popular and top contender for explaining that baryon symmetry in the early universe is through this electro weak field topological transition, not the QCD gauge field, but electro weak gauge field. And when you have such topological transition, just like what we have in the QCD sector, and coupled with the rapid expansion of the universe, that will bring the anti-baryon symmetry, frozen in your system. So that, in other words, so the physics is really kind of similar. We're at a very different energy scale. Of course, this is the electron-wave scale, this is QCD scale, but the physics is quite similar. So I think that also provides a way, to understand and probe this mechanism through laboratory experiment.
So
Okay,
I have a question about this. So by detecting the CME, what parameters are we pinning down in terms of this?
Very good. Essentially, we don't have a good control or theoretical understanding of this quantity. Like how many topological fractions you get in your collision, or which will offer the equivalent to say how many chirality you can get in your system. And that's something we hope that we can extract from measuring the CME. Okay, so there are many other related effects which I don't have time to discuss, and there are many other interests from different fields of research. Again, I don't have time to go through them, but just to mention that this is not just interesting to us. There are many reviews in recent times, and if you're interested, you can look into some of this to find more information. So now let me come to the search for this effect. I hope I convince you that this is at least interesting to look for. There are a few papers appearing from 2004 to 2008, which pretty much laid the theoretical foundation and motivated experimentalists to look for that, mainly from Dima Kajev and also collaborators. And then on the experimental side, Sergei Voloshin was strongly motivated to look for this effect, and he even developed a very important observable that's so-called gamma correlator, which is looking at the charge-dependent angle correlation between a pair of hadrons. I'll explain a little more, but this is the primary observable for us to look for this effect, and there are many variants developed based on that. Okay, so what do we expect in such experiment? Remember, chiral effect is required two things. You want a chirality difference, and you want a magnetic field. So do we have the magnetic field? The answer is yes. Actually, we have about the strongest magnetic field that you can find. Because those ions, like in gold-gold collision or lead-lead collision, you have a large ion with large positive charge, and they're moving almost at the speed of light. If you use your simple moving charge electromagnetic field calculation like this, you could immediately figure out that the field is really strong on the order of field times m pi squared. That translates about 10 to 15 Tesla. Okay, this is the more quantitative simulation of that magnetic field. You can see in the collision zone, if you average over many events, that magnetic field sitting there is very strong, and it's approximately constantly in this region, and it's pointing in this y direction, which in this 3D plot is the outward plane direction. Okay. There's an interesting trick to that. Of course, on average, you can see this magnetic field pretty much has a very well-defined direction, which is outward plane. But on an event-by-event basis, it actually fluctuates a lot. So around 2012, that's when I was a little worried about that, because that also was around time that people started to appreciate that how important the initial state fluctuations are for heavy-ion collision. So I took a look into this. I say, okay, maybe the magnetic field fluctuation needs to be carefully examined. Indeed, if you do simulation event by event, you will see that this is the magnetic field direction, and this is the event plane direction of your matter. Okay, and you can see that they're not always correlated. Actually, in the very central collision, this is the scatter plot of many events. In the very central collision, they're not correlated at all, and in the mid-central peripheral collision, they're much better correlated, and in the very peripheral collision, they're not very well correlated either. That the reason is simple. The eccentricity, that deformation, is dominated by participants, and the magnetic field is dominated by the spectators. Okay, so that's why you have this interesting pattern. But the lesson that's been taken away, that you should take into account that magnetic field is not always exactly pointing in your perpendicular to your matter plane. Okay, and that turned out to be a very valuable feature. So at that time, we say you should calculate this correlator, which is essentially a correlator or decorrelator between the magnetic field direction and your matter, harmonic flow plane, phi 2, phi 3, phi 4, phi 1. We did all those quantitative calculations, and that will eventually turn out to be a valuable feature. Okay, I'll come back to that at the end. But the short message is that we have a pretty good understanding of the magnetic field, at least at the beginning of the collision. 10 minutes? Okay, yeah. So what do you expect? Well, you have a magnetic field, you have this paramagnetic effect, which should induce a current in your quark gluon plasma that transport positive charge toward one direction, actually toward the other direction. And then those are blown apart by your strong expansion. In the end, in the momentum space, you have some extra charge going up and some negative charge going the opposite way. So that's what we call charge separation that we're looking for. So these are some nice plots, 3D, 2D plots showing what you're expecting. Okay, basically you're looking for a specific emission pattern of charged particle, same sign hadron preferably along the same direction, opposite sign hadron emitted preferably back to back in the magnetic field direction. Okay, so that's what you're looking for. And that gamma correlator I mentioned earlier is designed to pick up that pattern. Okay, you should see that difference in the gamma for same sign hadron and opposite sign hadron. Okay. So what happened is that the first measurement was reported by Star. It showed some interesting hint of that effect. And in the last decade, I think a lot of measurements were done by Star, Alice, CMS, at both RIC and RTC. The energy range of measurements span from 10 GeV to 5,000 GeV, and there are various colliding systems. So it proved to be a very difficult search. The main reason for that is that there are large backgrounds. So we're looking for some kind of charge correlation like this. Okay, but there are many other charge correlations that are present in the system. For example, your resonance decay, your rho meson decay into pi plus pi minus, that gives you a background, and you have local charge conservation, which is the hydrodynamic effect at freeze out. And that gives you similar patterns of charge-dependent correlation, and that is roughly scaling like the V2 of your system. It's like a bulk flow background. So really, we're redefining the question, namely, we want to separate those two, the CME and your background. I think I'll skip this because basically I want to say that it's not unusual. I mean, there are many difficult searching in physics. Okay, this is just one recent example. So we try all we can, basically. We also developed, so this roughly the status before the isobar collision from gold to gold, lead, cross beam energy. You have some good hints, but not conclusive. So that comes to the isobar collision. The idea was initially put forward by Sergei Voloshin, and then there were a task force to try to investigate the possibility of that. And the conclusion was that it's worth trying. The main idea of the isobar collision, I'm sure you're all already aware of that, is that your magnetic field, for the magnetic field, there should be a big difference between the two systems, ruthenium and zirconium, so that the signal which is driven by magnetic field should show some difference. Where the background is driven by bulk flow, and supposedly the two systems should be quite identical. That was at least the initial thought. So we have some theoretical tools that were built through the topical collaboration, the best collaboration around that time. The hope is that we have a tool to quantitatively study the signal and background. I think Shude here is one of the main contributors to this framework, even by AVFD simulation. We also use that tool and closely collaborated with the experimentalists from STAR in particular. We want to be prepared for that isobar analysis. Okay, so we took a deep dive into the observables, understanding really all how different observables behave in response to signal, in response to background, and things like that, and how we separate them. But already around that time, 2018 or so, I think some of you may already heard that from Fuchang talk, but that's when we start to have some worries about the uncertainty in the nuclear structure inputs. The reason that if you open the nuclear data book for, for example, ruthenium zirconium, you already see that the beta 2, for example, is not totally fully known for those two systems. Okay, so that was some concern. And then Fuchang took a closer look in collaboration with some nuclear structure theories, and then he did some calculation. That's from his paper. You can see that in certain situations, you would say that your naive expectation that the eccentricity difference between the two systems is negligible may not be really true. Okay, so that will first is a concern, because that will basically mess up with your overall strategy. We also were motivated. There were also, I think, around the same time, and at that time, there was also a hand-on collaborator. We had a paper about this. We had a proceeding in Quark Matter, in particular at Quark Matter 18. I was trying to alert the experimentalists that you have to take this into account. So that's what we did. We basically did simulation with different Woodstockson input. And indeed, you will see that in certain regions, like for example, the relatively central collision, you will see a large difference in at least several percent level difference in the eccentricity, which translates into V2 difference for two systems, depending on your nuclear structuring. Okay, so that certainly is concerning because your effect may not be big. It's already a very small effect, and if you have a few percent, uncertainty in that in your baseline, you are not going to make it. So we want to eliminate that. So we also actually propose a strategy, namely for the analysis, we suggest that to apply jointly the centrality and the multiplicity instead of using centrality. We suggest that directly using the multiplicity card and using the eccentricity or V2 card, so that you get two collection of events, ruthenium, zirconium, they have basically the same multiplicity, the same eccentricity or V2 distribution. In that case, our simulations show that can basically eliminate the V2 difference to be nearly zero, or your magnetic field difference between the two samples of ruthenium and zirconium are still at the level of 10 to 20%. So that would be ideal. So that's sort of the strategy we suggested. So based on that strategy, we actually did some predictions based on the simulation tool that we developed. So we actually systematically calculated the possible signature of the gamma measure with respect to reaction plane, gamma with respect to event plane, and delta correlator. So these are the relevant correlators where the CME is supposed to show up. You can see this axis is that theoretical uncertainty that Dean was asking. So you see, I don't know how much axial charge or initial kinetic imbalance I would have in the system. So that's that big theoretical uncertainty. So the hope was like experimentally then tell me that, okay, we're here. Okay, I saw that CME signal in this observable around here. Then that tells me how much axial charge I get in the beginning. All good until STAR released their results in 2021. Not only that, it was not showing a positive signal. It actually showed things that are totally opposite to any expectation. Okay, so you can see. So that's the STAR paper. Probably you heard about it. So the predicted baseline means that you assume there's nothing, just background. Okay, you assume the two systems would be identical. The gamma correlation, which is totally coming from background, would be equal. So that the ratio would be 1. If you do have CME, the prediction is that ruthenium will have a bigger signal because the magnetic field for ruthenium is bigger. Okay, so that would be greater than 1. Now you look at all the 5 different analyses, you can see they're all below 1. So apparently something goes very wrong. Okay, I mean, well, I'm not saying for experimentalists, but in some sense actually for experimentalists, because these are for particular centrality. Okay, 20 to 50%. Okay, because we already alerted them there are these issues. Okay, so it's better not to use centrality. That I think we made that message already at Quark Measure 2018. So indeed, I mean, it's actually the problem is self-evident from the same analysis because they showed very nicely that all the V2 comparison and multiplicity comparison between the system, they're obviously not identical. There are at least a few percent of difference. That's enough to destroy your baseline expectation. Okay. So that means that we kind of lost that key for success. Namely, we were assuming that, you see, why this is difficult? Because the background is overwhelming and signal is small. And we don't have a good, like 1% level quantitative calculation of that background. So the strategy was like, you have background 1 and background 2, if they are equal, I don't care how large they are, I just subtract. So that was the hope, okay? But that apparently apparent difference between the isobar system destroyed that hope. And even worse, that kind of conclusion in the STAR paper was really creating more confusion. That if the impatient reader, most people are impatient readers. Perhaps they'll jump down to the very last sentence saying no CME signal that satisfies the predefined criteria has been observed, or even worse, some people just pick up 3 words, no CME signal. That's what I encountered, I believe. Yeah. But then, you really have to say what is the predefined criteria and what that really means. Okay, they actually made it clear, but it's a method it doesn't get through. I think the prevalence is not applicable in particular in this case, shown by their own data. Then after that initial announcement, there were a lot of people looking into what it really means because apparently it's not even in line with the pure background. So you have to understand what happened. Of course, what happens is very simple that your background is really not here, but somewhere here, your baseline, because your two systems are different, you have taken into account their background are also different. So that ratio is not supposed to be as one. In particular, as I already mentioned, the background scale is roughly like 1 over charge multiplicity. So there is this one nut point here, which is the 1 over charge multiplicity of the experiment, the ratio between ruthenium and zirconium, that's around here. If you are serious, you take this as your baseline, you will then claim victory because all points are above it, okay?
Why is that background, that new background line the same for all of these different observers?
No, these are just different ways to measure that gamma correlation.
So kappa 112 is gamma 112 is in disguise, and K2 is kappa.
That's right. These are like 5 different independent analyses. They use slightly differently defined observable, which should give you the same information. And in particular, this is the ratio between ruthenium and zirconium.
And the fact that they are measured in different ways does not affect their expected background value.
Because you're taking a ratio again. For each specific observable, your background fraction may be different, but you're taking a ratio between ruthenium and zirconium. So again, the idea is that baseline, if you are correct about your baseline, then whatever observable you use.
We have looked at the ratios of observers for 3 weeks now, and none of them are constant. They all impact parameters.
Okay, yes. Of course, if you are more serious, then yes, for each observable, you have to be looking under the hood more. Yeah, that I agree. Well, no, but that's not the end story. So now here you see. So then I think Jiang Yun and Jian Chun, they quickly realized that actually was the opportunity for understanding better the nuclear structure. I'll try to finish first. Using different nuclear structure inputs to try to describe that multiplicity. I think this was their paper. So we want to understand the baseline better. So we use our simulation, but using the nuclear structure input from them. And you can see you actually can describe that charge multiplicity ratio in all those centralities between the two systems. So once you have done that, so the lines are calculating, the dots are the experimental data. So you can see you can reasonably capture that multiplicity difference between the two systems. Once you have done that, you can run your simulation without CME signal to give a baseline, and you can take a ratio between them. So this is for the gamma correlator divided by V2. This is for delta correlator. In both cases, you can see the baseline and the experimental data have some room for CME signal. So I want to make this message short. After taking into account that multiplicity difference, data versus baseline shows some room for that CME signal. And you can do a more quantitative analysis by saying, what is the signal ratio? So the idea is very simple. You have a ruthenium, you have a background. Now, background and background are not exactly the same. They differ by a factor, and this is dominated by the multiplicity difference. Okay, if you have a good handle on your multiplicity difference like this, then you can quantitatively say the background ratio should be like 1.05. The signal ratio is controlled by magnetic field, and that we calculated already. So we have a ratio between signal. Now, depending on your signal to background ratio, the overall ratio will change. Okay, the idea is simple. If you have, say, 0 signal, then that will be the final ratio. But if you do have signal, you'll have overall ratio that's this, like this.
Can we go back to the last slide? I think now you're making committing the same sin as you have accused some of us to. You said on the previous slide there may be room for CME sequence contribution, and then at the bottom you conclude there is a CME sequence contribution.
Maybe I don't.
Just look at the last line there. You are claiming discovery here.
No. I mean, cool. I mean, I'm not saying that. Well, that's fine. I mean, even with our paper, your report, we got a complaint like that, and we made it reasonably clear in the paper that we're not discovering it yet. Okay. No, there's a room for that. Okay.
Yeah, but if you don't want to be misquoted, you should really.
Sure. Okay. Yeah, I can check that. But here you can see there is a more quantitative statement actually in the paper. Okay. The quantitative statement is that if you do this analysis based on those assumptions, that's what you get. The CME signal fraction is 6.8 plus minus 2.8. So that means roughly you have perhaps about 2 sigma level of room for that signal. Okay. So that's the statement, quantitative statement. I think I'm going to skip this, but I just want to say that experimentalists like Pochang and also Pritzvich back there, they independently perform their own kind of analysis similar to what we tried. I think the method is coherent. So back in early December, we had a small cardiology retreat at UCLA, sit down and discuss. I think we had a consensus that in the isobar system, there is probably room for signal, but it's going to be very, very hard to push the significance to beyond something like 2 sigma. Okay, the main reason for that is this so-called non-flow effect. So this is, for example, from Fuqiang. He perhaps gave a talk last week. The so-called non-flow effect it's very hard to quantitatively, calculate or extract from experiment. So if we're able to push that, 1% level of non-flow effect, then we can do better. But for now, we're not there yet. So 1 to 2 sigma is about what we have. So I'm going to skip this because I want to say one few words about the what's next. So one of the things I do want to point out, which was perhaps also presented by Fuqiang, is that you do have a much better, actually bigger signal in the gold-gold collision. Again, so gold-gold collision has a larger signal, but isobar system has a better contrast capability. So that's why we like both. In the gold-gold case, yeah.
What you really mean is if there is a signal in ruthenium, there should be a larger signal in gold.
Correct.
You don't know for a fact.
Yeah, from a theoretical point, yeah, that's right. No, okay, yeah, but now this is the experimental analysis. It actually leveraged that correlation or decorrelation I mentioned earlier. The B field is correlated better with your calculation frame, the reaction plane, or less correlated with your matter geometry event plane. So you can do your measurement with respect to the reaction plane and then with respect to the event plane. By doing that contrast, you get also a handle on whether there is a CME signal or not. That method was studied for the purpose of for the isobar, but now since we have this understanding of that behavior, actually you can use that back for the gold-gold collision. And they apply that to gold-gold collision, this was the paper from Star, very, very recent after this isobar. You do have actually 1 to 3 sigma level, depending on specific ways of removing the non-flow effect. You could get another 10% fraction of the CME signal in the gold-gold. So that's very encouraging. Again, maybe overall you may say 1 to 3 sigma, that may not be enough for discovery, but that's fine. And also I think Friedrich, perhaps I don't know if you're going to talk about it, but there are also efforts and lower beam energy like 27 GeV and 19 GeV, which also shows some hint of signal. So I think the main message that as you all know that in 2023, this year to 2025, there will be a large data set of gold-gold collision at rates that will be taken. And the hope is that many of our friends here in the STAR will continue this effort and analyze that formidable large amount of data. And I think there is a big hope that maybe we'll come back and say CME at 2027. So stay tuned. Thank you.
Over time, we could probably take a few questions. We've already had some, so maybe that's sufficient. I don't see any more. Do you?
Could you talk a little bit about? I know there's a condensed matter observation of this. Can you talk a little bit about that? There's some condensed matter system.
Okay. Yeah. So in the condensed matter system, that's mainly about the so-called semi-metal. In those semi-metal, so but in the condensed matter, they don't really have something like what we call the chirofermion. But they do have something. So they do have you may say it's like quasi-electron state, which has a momentum and a spin correlation. And those states behave, if you write down effect quantum description of them, they behave like Dirac particle or the wild particle, and they're like 3D samples. And then in their case, they got the idea that there should be anomalous transport. So what do is that they pump the mu field. They have a much nicer situation. They just apply magnetic field, electric field. That's through the anomaly will pump this anomaly. That's this equation basically. If you apply electric field and magnetic field parallel to their sample, then chirality starts to be generated. Your quasi-electron state will have a right-handed state. So that's how they generate this mu5. So that's kind of basically controlled. And then they apply additional magnetic field to induce this current, and they can measure this current. So those experiments were done around 2014, 2015 for both three-dimensional direct semi-metal and wire semi-metal.
Okay, oh, we have a remote Zidu on Zoom.
Yeah, so I have a very simple question for Jinfeng. Yeah, first, nice to see you again, Jinfeng. So I have a question relating to those Wood-Saxon densities that you showed in one of your slides. Could you go to that slide that you have maybe 3 different colors about your Wood-Saxon? Yeah. So, so I just want to understand what exactly are those kind of the nuclear structure information that matters for those epsilon 2 and the BSQ. So yeah, I just want to understand the difference between those black and the red and the blue curves. What's the difference between these Wood-Saxon 1 and Wood-Saxon 2?
I couldn't tell you out of my head the numbers, but I can tell you what that those are 3 different Wood-Saxon, let's say. Actually, the first Wood-Saxon is perhaps the standard Wood-Saxon. I think that I forgot what do I mean by standard Wood-Saxon, but perhaps without the beta 2. And then the Wood-Saxon 1 and Wood-Saxon 2 are 2 different sets of beta 2 values, and also I think also the slight different R values for the ruthenium and zirconium. If you look up the data table, I think they are not fully settled. There are like 2 sets that are possible.
So it seems that the description of the deformation of those nuclei matters for your CME relating quantities.
What do you mean? Can you say it again?
Because my understanding is that those beta parameters are describing the deformation of the nucleus, right? Mm-hmm. So it seems that we are changing those beta parameters, and then correspondingly, those curves are changing obviously. So which means that how you are describing the deformation of the nucleus matters for your CMU relating quantities.
Well, sure. I mean, not only that, it matters for even flow and so on, right? People here were discussing basically, you use different input parameters, you get different flow, different multiplicity, and indeed that means that you can turn around and use Hawaiian data to put some constraints on those.
Yeah. Okay. So does the, for example, the nucleon radius change in those 3 Wood-Saxon form?
For what?
The radius of the nucleon, the IMS radius of the nucleon.
For nucleon itself, okay, that's a good question. I think we perhaps in this simulation, in this particular simulation, we use some standard value like 0.5 Fermi of smearing in the Monte Carlo Glauber. But that could have some, there could be an additional parameter that may bring some impact. I think there were some discussion that this worked about that.
Okay. Okay.
Yeah.
Thank you.
Yeah. So talking about these geometry issues here. I mean, if there's any information about the nuclear geometry, isn't it mostly coming from measurement of quantical, measurement of electromagnetic moments? I
would think so. Yeah, it might be from the electron scattering experiment, right?
Right. Well, it could be from gamma ray transitions and things like that. Question is, of course, what assurance do you have, or what allowance for the possibility that neutron deformation can differ from the charge deformation?
Very good.
Yeah, and do you have any feeling for how big those deformations could differ? I mean, you could do inelastic scattering, which will not by Coulomb excitation, and you could try to infer information about that, but that may be difficult to do at the level of precision that you need. Do you have a feeling for how close these electromagnetic moments have to map both the charge and the matter distribution. And then there's the other thing that these electromagnetic moments are not just measurements of charged surfaces, they're measurements of charged wave functions. And so they have different magnitudes in the interior as opposed to in the exterior of the nucleus. What sensitivity or how carefully do you have to know the actual charge distributions in there? And then therefore, how carefully do you need to know the neutron distributions in order to make your experiment work?
Those are very, very good questions. I think in the magnetic field itself certainly is basically dictated by the proton distribution. So certainly there is a sensitivity to that. How large that sensitivity is, that's a question that I don't have an immediate answer. We at some point tried some simple.
But the problem is that the dirt effects, about determining how central is your collision doesn't come from the signal, it comes from hadronic physics, right?
Sure.
So you rely on the hadronic physics giving you information about the geometry, and then the question is how well can you put constraints on the hadronic physics just from information coming from the electromagnetic sector?
Let's take the last question real quick.
Okay, Yifan, you mentioned on your last slide about the future plan, you mentioned that you're going to extend the search for low energies, with the BES, the power plant. What do you expect to see any advantages at the lower energy, where your magnetic field will be reduced, but reaction time will last longer?
Yeah.
Factors play.
Sure. That's actually a good question. I probably brought somewhere here. So there was some so in general so here when you go from high energy high beam energy to low beam energy, the peak strength of the peak strength of the magnetic field will decrease. However, generally it's understood that the magnetic field duration will be longer. So chances are actually in the extreme high energy that magnetic field is so short-lived that it won't generate much. So when you go down to break beam energy and even lower, like say to 62 GeV or something like that, you practically have the best magnetic field, overall effect of the magnetic field. But on the other hand, when you go to really low energy, you're turning off your quark-gluon plasma, and then that effect will be gone. So basically, our expectation is that it kind of go up and go down, something like that. That's our expectation of that beam energy dependent. Thank you.
Thank you.